Welcome to today's virtual seminar, Water Activity 201, Microbial and Chemical Stability, presented by Brady Carter, Research Scientist here at Decagon Devices.
Thanks, Rhea, and thank you for the opportunity to be able to talk today about water activity and its influence on microbial and chemical stability. The goal of today is to be able to provide some in-depth detail about how to utilize water activity. We have Water Activity 101 that talked about the theory of water activity and how it's measured, background information about water activity. Here in 201 we want to actually start taking the water activity numbers and applying them and making use of them to do some modeling work and be able to do predictions of shelf life based upon microbial stability as well as chemical stability. So the two applications that we're going to focus on today are water activity that are affected by water activity are microbial growth and chemical stability. So starting out with microbial growth, and this is probably what water activity is best known for, is its ability to be able to control the growth of microorganisms. And this work's been known, or this work was done originally in the 50s, 1953 and 57. Papers that were released by Dr. Scott showed that there was a limiting water activity below which microorganisms would not grow, and that limiting value was going to be specific or unique to each type of microorganism. And it was water activity, not moisture content, and that was what they had been trying to use up to that point to try and link up to microbial growth. It was understood that those microorganisms required water, but for some reason the water content wasn't giving them very good correlations. And then once they went to water activity, then those correlations were much better. So just an example here of what those limits are for different species of bacteria, and we'll show some for yeasts and molds as well. Keeping in mind as you look at these minimum levels, these are the minimum water activities with all other conditions being optimal. So optimal conditions for pH, temperature, all nutrient content, competitive species, all of those things are in their optimal level for the growth of that organism. And the only thing that's being varied is water activity. So this truly does represent worst case scenario. This is the lower limit for growth for these organisms. They may actually stop growing at water activities higher than what's shown here if you combine the effects, synergistic effects of different types of or other factors such as, like I said, pH, temperature, etc. So these values represent the values of water activity that if you get below these water activity levels, these organisms are not going to grow regardless of what other conditions are that could contribute to the growth of the microorganism. So you see listed here several different types of bacteria. Pathogenic bacteria, of course, are of the most concern in terms of microbial safety because they can get people very sick and even lead to death. And you'll see the main culprits here shown, your E. coli, Salmonella, botulism, Staph, Listeria, and you can see where their individual lower limits are for their growth. Now it's important to understand at this point that what these limits are is for growth or proliferation of the bacteria. They are not a sterilization level. In other words, if you move to water activities less than what's shown here, does not mean that you've removed any kind of contamination from a product or sterilized it. This is not a kill step, lowering water activity, it's a control step. It prevents the proliferation or growth as the product is stored or shipped or sits at a consumer's location. It prevents the growth of microorganisms to levels that could cause an infection, so the product remains safe. But it doesn't remove the potential contaminants, and microorganisms, especially pathogenic bacteria, can survive very well at low water activities, as we'll see in just a moment. So keep in mind that as these lower limits are shown, these are for growth and not for sterilization. And here we show the lower growth limits for molds. You'll see that for most types of mold species, they can handle lower water activities than the bacteria can, so they have a better ability to survive osmotic stress. And you can see that most of those species, a majority of them, stop growing at less than 0.7 water activity. And this is called the practical limit for microorganisms. The growth of microorganisms is this 0.70, and that's because the only thing that grows less than 7, between 0.6 and 0.7, are some xerophilic molds and osmophilic yeasts, such as the example that's given here in this list. So, but most of the organisms, the mold organisms that would be responsible for spoilage, are going to stop at 0.70. And then for yeasts, lower limits up in the 0.80 range for most types of potentially spoilage organisms. Sometimes yeasts are beneficial and you want their growth, and so that can also be controlled by water activity. It just has to go in the other direction. And then of course below 0.7 is osmophilic yeasts. And just a quick note on water activity and utilizing water activity for control of microorganisms. We did some investigations here at Decagon where we looked at, we've been processing and developing cured meat products so that we could learn about that process, learn more about what happens in real conditions when you're actually trying to process and make these products. And when we did that, we did see a mold problem. And it wasn't the mold that we wanted to grow. There is certain types of mold species that you want to have on these types of products because they help with the whole process of fermenting and the development of the cured meat. But because we had the humidity too high, we didn't make conditions right for the good mold, but we did make it right for problematic molds. And because we didn't have a nice proliferation of the good mold, there was no competition. When we removed the undesirable mold and went to a lower humidity by making those conditions more prime or more ideal for the growth of the beneficial mold, then we were able to keep that mold collinated and prevent the growth of the mold that wasn't desirable by keeping the conditions prime for its growth. So there's lessons to be learned about water activity when you try to do this in practical application. That's always a different experience than seeing it on paper, but it does work. It really does actually work, and we were able to show that and learn from our experience as well, just like I'm sure all of you do as you take these applications that we talk about and apply them to each one of your individual products. So let's talk a little bit about what this mode of action is and how does water activity prevent the growth of microorganisms. And it's through the application of what we would call osmotic stress, where the pressure, the osmotic pressure inside of a microorganism has to be maintained at a certain level in order for it to thrive, to grow, or to be able to reproduce. It requires moisture for that process. It requires it to be able to maintain its turgor pressure, to be able to maintain all the things, the metabolism mechanisms that has to happen in the organism. So when it's exposed to conditions where the water activity of its surroundings or its environment is lower than the water activity of its interior, then it's going to experience this osmotic stress. And water is going to move from high energy to low energy, so from high water activity to low water activity. These microorganisms rely on being able to move water across their membrane into the interior because of those energetics. So when they're exposed to osmotic stress conditions, then they start to lose water to their environment. And so they only have a couple of choices under those conditions. One is to try and lower their water activity, to try and match the water activity of the environment so that they could stop the outflow of moisture that could eventually lead to death, but it will certainly stop their metabolism and growth. And so some microorganisms are better able to do this, to lower the water activity, than others. So each one has their own individual level of defense mechanisms for desiccation. And some of them can produce, within the organism itself, they can produce solutes that they can then maintain inside of their cell membrane that will lower the water activity. And these are typically polyols, sugars, amino acids, and that by having a concentration of the solutes, then the water activity comes down because of the interaction that they have with water. Now, some types of microorganisms don't have the ability to be able to do that, and so they have to try and move some of these solutes across their membrane from their surrounding environments. And again, each one of them will have a unique ability to do that. But if they go through that process and they still aren't able to lower the water activity down enough to be able to maintain their conditions, or so that it's equal to or less than the environment that it's being exposed to, then their really only other choice is to then basically go into a dormant stage. And so they try to secure themselves by restricting any more moisture loss from the organism, and by shutting down all of their metabolism to be able to tolerate these desiccated conditions. And like I said earlier, some are better able to do that than others and can survive very well under very low water activity conditions. They can form spores that are very hardy and can survive these extreme types of conditions. But the point is that when that happens, they are no longer proliferating or growing. They're not replicating so that they could get to high enough levels that would cause an infection if the product that these were on happened to be consumed. So that's how the growth is slowed, by lowering the water activity. You basically put stress on the organism. The organism has to respond. If it's not ideal conditions, its growth will slow, and then eventually it will just stop, and the organism has to try to use some sort of a defense mechanism in order to assure its survival. And that is at the cost of not being able to replicate anymore. So shown in terms of a growth curve, keeping in mind that the y-axis on this is logarithmic growth, you can see that as the water activity is lowered, the initial stage, lag stage is increased. The growth stage is the rate of that growth is severely declined, and then its final or resting level is much reduced from that of higher water activities, such that that level that you see for 0.87 is now below the infection level for that microorganism. So not enough organisms were able to grow under those water activity conditions that could cause a problem, but they were. It was possible to have microorganisms proliferate to numbers that could cause an infection at the higher water activities, even at 0.90. So you can see what the effect is of having this osmotic stress. The organism basically just has to, overall it has to shut down, and it affects its ability to be able to replicate and proliferate, and hence you get the control of microbial growth due to the water activity. So here's some examples of what we were talking about, where organisms can survive very well at reduced water activities. You can find viable salmonella in chocolate at water activities as low as 0.3, in peanut butter and water activities as low as 0.5, and salmonella and staph in powdered milk at water activities of 0.26. So they're likely not going to be present in high enough levels to cause an infection unless you have an inoculant that comes in while it's sitting in storage, and then they'll still cause an infection, and that's usually a result of violating good manufacturing practices. But keep in mind that if these were to survive in these low water activity products, they're not in levels high enough to cause infections, so they would never show themselves as to be a problem. But if they're there and they're present, keep in mind that something like chocolate, peanut butter, powdered milk, these are all ingredients that are going to go into some other type of a product. And when they go into that product, they're going to experience most likely very high water activities as they're mixed together and as they're added as ingredients. As a result of that, when they experience that high water activity, if that water activity is high enough now for them to grow, they will, as happy as can be, start to grow again, and could grow and proliferate to levels that would be problematic and cause an infection, even though they were very controlled and were not growing when the product was in its ingredient state and was dry. And because of this, there's a lot of emphasis now on figuring out how to effectively sterilize very low water activity types of products like powders. Is there an effective way to be able to make sure that there's nothing left in there that's viable that could start to grow again? And there's this work being done in several locations, one of which is Washington State University, that's here where Decagon's located in Pullman, Washington, in cooperation with Michigan State. And one of the things that they are investigating is what is the role of water activity in that, in the effectiveness of the processes that will occur. And so from that will be found an ideal water activity for a given organism to make sure that it's possible to be able to sterilize it in its very dry condition. Because of its importance in microbial control, water activity has become a big part of government regulations to limit or prevent contamination of food products by microbial spoilage. It's part of the definition of potentially hazardous foods. It's incorporated into several Code of Federal Regulations as critical parts of being able to make foods that are safe. It's a critical control point in HACCP plans, and with the recent changes to the food safety laws, where an emphasis is now being placed on good science and having good prevention in place, and an emphasis on creating HACCP plans, this becomes very critical. Moisture content is not an acceptable critical control point. Water activity is the only moisture-related critical control point that assures that a product will remain safe. And it's also included in several parts for pharmaceuticals, such as USP 1112 and in ICH guidelines. And one of the exciting aspects of the use of water activity has come through development and research in the area of hurdle technology. And basically what this is if you put enough hurdles in front of a microorganism through different controls such as water activity, temperature, pH, you'll see a list of all the different control mechanisms listed on the right there. That through a combination of these, if you put enough hurdles in the way of a microorganism, that you can prevent its growth. So this is the whole concept behind the HACCP plan. Each one of these hurdles would, in a sense, be a critical control point. Now, for some types of products, such as in example number 3, the only control point that was needed there was water activity. It was giving the level of control that was needed, so that would be your critical control point. But in number 6, water activity by itself was not enough. And so you needed some additional help from having a lower pH. So in this case, your critical control points are both water activity and pH, and so forth and so on. So what this shows is that these different elements can work synergistically to stop the growth of a microorganism, and at times, by having a combination of these effects, you can have control at higher levels for water activity as well as for pH and etc. And so the development of that hurdle technology has led to the current definitions for potentially hazardous foods within the FDA Food Code. And the first table is Interaction Table A, and this is for those manufacturers who have a kill step on their product and then subsequently package it with good manufacturing practices to keep that product sterile after having had the kill step. And if that's the case, then anything with a water activity less than 0.92 is considered to be non-potentially hazardous. It doesn't have to be time temperature controlled when it's being shipped or stored. Vice versa, if you have a pH less than 4.6, then it doesn't matter what your water activity is, that food is not considered to be potentially hazardous. But you could also have a water activity in the range of 9295 if you combined it with a little bit lower of a pH, and that food would still be non-potentially hazardous even though it's above the lower limits for both pH and water activity. So these are very useful information, and tables should be something that you have definitely within your quality control and quality assurance. And certainly something that research and development should consider when they're setting process controls and the release specifications for any product that's being manufactured. What is that critical water activity and pH of your product? Are you going off just water activity, or are you going off just pH? And where do you, what cell do you lie in this interaction table? And so having these interaction tables available to you and printed out is probably a very important idea. Table B is for manufacturers who don't have a kill step, or that do have a kill step but then don't package to assure the sterility of the product. Or if you just want to be really conservative, you would go off of this table. So in this case, the lower limit for water activity is is dropped down to 0.88. So a little bit more stringent in terms of what's allowable and considered non-potentially hazardous. And that if you're less than that 0.88 value, then you're considered non-potentially hazardous regardless of what your pH is. Vice versa, if your pH is less than 4.2, now down from 4.6, then you're considered to be non-potentially hazardous at any given water activity. But again, you can have higher values of water activity and higher values of pH and still be non-potentially hazardous. So it's important to have the table and link up the values that are specific to your given product. So now I want to talk a little bit about how you would do some modeling for microbial growth. And we get this question quite a bit. Is it possible to be able to predict how much growth of a given microorganism you might experience under specific conditions? Of course, the hope is that there's one equation that does that for every organism and every situation that you might deal with. But like with most things, that's not the case. The models that are developed, and what they are is an equation that does predict the growth or survival of a microorganism. But these are typically empirical equations that are very specific to the product, to the microorganism of interest, as well as what the preservative or humectant is that's being used to control water activity or control growth. So they have to, in order to be able to make this useful, you do have to do a little bit of initial setup and initial work for your given product. What we present here for both microbiological modeling as well as what I'll present for chemical stability, keep in mind that these are principles that we're passing along. And these are templates for how you would create one of these studies and run them. They're not meant to be values or examples that you would specifically be able to take and apply to your situation. It's simply to give you the instructions, the ideas, the principles about how you would go about doing this process, and then you take those and you use them in your facility or your location and work with your given product. So you are going to have to collect some information, but the pathway or the model that's being set up by, the methodology that's being set up that we describe is what you would use, or you can use that same type of pattern in order to generate the models that will be appropriate for your given situation. And so these kinetic models that we develop are used to and capable of predicting the rate of growth based on a set of environmental conditions that potentially could be exposed to. Growth boundary levels specifically describe the limits of conditions that allow or do not allow growth. And so in this case, what we're predicting is time to growth as opposed to an actual rate of growth or amount of growth at a given point in time. So this is kind of an on-off situation. It is possible to do modeling directly to rates of growth and figure out how much growth has occurred. But in terms of shelf life, what's often useful is if you say, oh, we're not going to allow any kind of growth, so as soon as growth starts, that's the end. That's where the cutoff is. That's where shelf life ends. And then it's kind of an on-off situation, as I said, and it makes it a little bit easier to do the model development. So here's an example of how you would set up the experimental design for one of these experiments. So you would have a broth, and you might have a broth at several different pH values because pH is one of the factors that affects the growth of microorganisms. So you want to be able to combine the effects in your model of pH as well as relative humidity and possibly humectant level, humectant type, preservatives, having preservatives in or not having them. So you set up your experiment. So in this case, you might have some potassium sorbate that's also that's varying as well to see what its effects are. And then you're going to have pick a particular organism that's of interest. And you do need to do this specifically to each organism, as I mentioned earlier. And then you're going to do some sort of a screening method to figure out whether or not you've had growth or what your rate of growth is. And so in this case, in the example that I'm going to show, they used optical density, and this is work that's come from Cindy Stewart, published in 2010 and used with her permission, where an example that they use for doing some of this microbial modeling. And so what they used is a bioscreen system where they looked at optical density, and once the optical density was greater than 0.35, that indicated that there was growth, and that was the cutoff level. That was unacceptable. So what they were finding is how many days would pass. They were trying to predict how many days would pass under a given set of conditions until you reached this 0.35 level, which indicated growth. And so then you can see how they set up with 8 replicated wells, duplicate studies, how many wells they monitored, and the conditions they used. They incubated at 37°C for up to 6 months. So here's their growth curves as indicated by the optical density. So keeping in mind what was indicated, that at 0.352, if you were above that level, then that was considered growth. And so you can see for each one of these particular wells that are described here, the line drawn across at 352 is an indication of growth and how much time it took to get to that growth for each one of those particular microorganisms. So with that information in mind, the next step was to actually develop the models to predict the time to growth as a function of pH, relative humidity, and preservative level. And you have a time series now for each one of these, for each one of the samples or each combination of sample and that was evaluated. So that you know how much time it took under those given sets of conditions and combinations to reach growth. In this case, they use sensor data, which requires special analysis using the lifereg function in SAS. And then they used these prediction equations to construct contours for the growth boundaries of this particular microorganism. Once the model was created, then it was possible to actually create a graph that would show where growth would occur and where it wouldn't based on a combination of conditions. So here's an example of what those models look like for 3 different humectants: sucrose, fructose, glycerol, and sodium chloride. Notice that within these models, and these obviously aren't just simple models, they're complex equations, but within those models are relative humidity or water activity, pH, and preservative level, so that you could plug in a particular value for any given for the microorganism of interest here, which is staph, for a particular humectant that's being used. You can put in what your water activity is, what your pH is, and what your preservative level is, and it will tell you, you take the, raise it to the exponential or take the exponential of that, and it will tell you what the amount of time was to be able to get to growth. So from that, they were able to develop these contour lines. So you can see that the contour lines represent time to growth from 30 to 180 days. So on the less than 30 days, you have growth in less than 30 days. That's the bad areas. And then if you move over to the no growth beyond 180 days that was considered to be no growth, then that's the area that you would want to be in to be able to maximize shelf life. So you can see the range where you have no growth is at low pH, low water activity, but there are, even at high water activities, if you lower the pH, you can have no growth, as well as at high pH or neutral pH, you can have no growth if you lower the water activity. So again, this is an illustration of how these interactions between pH and water activity work, and how they set up boundaries for where you have growth and no growth. So from all of that work, what they did in this case was they implemented this into a nice, easy to use Excel sheet where the equation, those models that they developed are built in right into the equation, or right into the Excel sheet. And again, this is specific to the humectant combination or humectant that was used, as well as the microorganism. But with those in mind, you can plug in here your water activity, your pH, and your preservative level, and it will provide with you how many days it would be until growth occurred. In this case, in the example shown, that's 1.7, and that is not an acceptable level of shelf life, and so the outcome is that that particular combination would fail. Now, if you change the conditions to lowering the water activity, having a neutral pH and no preservative, by lowering to a 0.87 water activity, now you've extended the day to growth to almost 1,000 days, and that would then be considered to be safe. So by having this program set up, you could take any conditions, apply them to them for this particular organism and humectants in this given product, and know immediately whether or not that shelf life to when that microorganism would grow is going to be acceptable or not. So that's valuable information. It is possible, again, to do this for your given product. Take the principles that we've applied here and then use them specifically to your product and your situation, applying the appropriate appropriate models that you develop from that work. So now moving on to chemical and biochemical stability. Microbial safety isn't always what ends shelf life. Shelf life can be ended by other degradative types of reactions. And sometimes those are chemical reactions that occur that cause the product to not be desirable. And examples are Maillard-Browning reactions, lipid oxidation, hydrolysis reactions, often leading to nutrient degradation, enzymatic reactions, and then enzymatic stability. So one of the most important steps for if you want to try and determine the shelf life of your product is to figure out what it is that ends shelf life. And this is an often skipped step in this process, but obviously it's vital and absolutely necessary. But I've often asked people what ends their shelf life, and I don't get any answer back. And it's really hard to determine what your shelf life is if you don't know what the event is that ends shelf life. So is it microbial growth that ends it? Is it browning of the product that ends it? Is it off flavor, off odor? Is it loss of texture? What is it that ends shelf life for your given product? And once you figure that out and you come up with some way of being able to quantify whatever that is by the production of a product or even possibly sensory information, then you have the capability or the possibility of being able to model what the shelf life is going to be based upon the rate of that reaction, that particular reaction, and find conditions where it's minimized. In general, and you can see from this stability diagram that's shown, as you increase water activity, there is a general increase in reaction rates, whether it be any of the reactions shown. In general, the rate of reaction will increase as water activity goes up. Now, if you want some specific information about each one of those reactions themselves and how they proceed, I would invite you to be able to reference any kind of a food chemistry textbook, and they have them in detail there, what all the intermediates are. But in general, what we're saying is that in a lot of cases, those reactions that were shown are going to be detrimental to your product. They could end its shelf life. So you're going to want to be able to figure out some way to be able to minimize their effect. And that's done by modeling and figuring out what effect is the conditions that the product's being exposed to having on the rate at which that reaction occurs, and how quickly will it have reacted or proceeded forward to a level that ends the shelf life of the product. And when we talk about kinetics of reactions, typically most reactions fall into either a zero-order model or a first-order model to describe the kinetics of the reactions. And in these equations, the values, the A values represent concentration and concentration at time zero. T represents time, and K is the rate constant for the reaction itself. And you can see there that the relationship between them is dependent upon whether it's a zero order or a first order. If you want to know if it's a zero order or a first order, the best thing to do is to plot the concentration of the reaction reactants or the product of the reaction, depending on whatever it is that you're tracking. So this may increase if you're tracking the product, or decrease if you're tracking one of the reactants. But if you map concentration versus time, and that relationship is a straight line, that's an indication that you're dealing with a zero-order kinetic reaction. And the minus slope of that plot will tell you what the rate constant is, which is reported in concentrations per day. Now, if it's not a straight line, and then if you were to plot do a logarithmic plot of concentration versus time, or if you were to plot the natural log of time versus the concentration, and that comes out as a straight line, then that's an indication that it is a first order kinetic plot. And in this case, if you want to be able to find the slope, then you just need to, or sorry, if you want to find the rate constant, then you just take the minus the slope and multiply it by 2.303 if you're using a logarithmic or base 10 scale to get it into natural log. And then that value or that slope is going to be equal to your rate constant. So when you do shelf life modeling for chemical reactions, you have to account for both temperature and water activity. And a lot of the work that's been done in this area has been focused on temperature and temperature effects. And from that you get what's called a Q10 value. These are Arrhenius types of relationships Arrhenius types of, or the equation focuses on tracking the temperature effect on different types of reactions and whether or not they follow those Arrhenius types of kinetics. But in reality, there's both water activity and temperature both having an effect on the rates of these reactions, and accounting for just temperature leaves out half the story. It is best to use data collected on your product, not try to use data collected on a different product, even if it's close, and try to use that for doing these types of modeling. You do need to have a way of being able to quantify and track the progress of your reaction, whatever that may be. Might be a way to be able to track oxidation through the consumption of oxygen or through the production of a product. And there are oxidation testers out there that can be used for that. You may have to use something like HPLC to track the concentration of either a reactant or a product. Sometimes there's even kits for vitamins. There's kits that you can use to track the presence of vitamins. Once you've collected the data at different conditions, then you can use that information to create empirical models that account for both temperature and water activity. And this is most easily done through a combination of the Q10 and QA effect. And just for your information, there have been those who have tried to modify the Arrhenius equation to account for water activity or percent RH to try and incorporate the elements of both. Although there's not that's very specific to the situation that they were dealing with, and so the efforts go on to try and even create better models to truly account for both temperature and water activity effects on reaction rates for these different types of products. So here's an example of first of all, what you would do for the temperature effect. So reaction rates increase as temperature increases. Again, that's been modeled most typically by using Arrhenius equations to be able to create a model that will account for temperature effects. You can also then apply that easily into what's called a Q10 approach. And while what Q10 is a factor of how much the shelf life will change due to a 10-degree change in temperature. We're 10 degree higher or 10 degree lower. What impact does that have on the shelf life? And that factor then can be applied for any given situation. You simply figure out how much of a temperature change have you experienced, and then adjust the factor for whatever level of change you've occurred. If it's 20 degrees change, then it would be 2 times that factor, and then apply that, either add it to or take it away from the shelf life under the conditions that it started, and then you would be able to get the new shelf life. Water activity uses a QA concept, and this is a little different but very similar to the Q10. In this case, what we're talking about is how much the shelf life changes for a 0.1 change in water activity. And so if you know the shelf life or half-life at a given water activity, and then you divide that by what the half-life or determined half-life or shelf life is at 0.1 water activity higher, that factor, that ratio, is what we call the QA. And so if you had a 1.5, a QA of 1.5, that means that for every 0.1 change in water activity, you're going to change your shelf life by 1.5 times. So if it's 30 days, you're at 0.3 water activity. If you decrease it to 0.2, then by a factor of 1.5, your shelf life will increase from 30 to 45 days, and 45 to 68 if you have another 0.1 decrease. So what this shows is that it is possible through collection of data to be able to identify a factor that's due to water activity and how it directly influences the shelf life based upon the reaction rate of some sort of a degradative type of reaction. So how would you go forward with doing this for your own types of products? So here are the steps. The first step would be to identify the primary mechanism that's responsible for shelf life in your product. What reaction is it? Then try to obtain some example of your products that's as close as possible to the commercial product. Figure out how you're going to analyze for the extent to which the reaction has proceeded or occurred, and also where are you going to draw the line? Are you going to say that if it's changed, or you've produced the 50% more of a product, or that the reactant concentration is decreased by 50%? Is that where shelf life ends, or is it less or more than that? So that you can identify exactly where the end of shelf life occurs. Then you need to take these samples that you've obtained of your product and expose them to a combination of 3 temperatures and 3 water activities. So you make up a matrix and do a connection between those, so that at any given temperature the sample experiences all 3 water activities, and then vice versa, any given water activity experiences all 3 temperatures. So you'd have 9 different combinations of water activity and temperatures to collect data. You can try to speed this up through what's often called accelerated shelf life testing by using higher water activity and temperature conditions, just keeping in mind that doing so could result in phase transitions, could result in changes to the product that aren't representative of the product itself, and that could have an influence on the results, especially if when you try to extrapolate back to room conditions or normal conditions that it might experience. So here's an example of how you would do this process for shelf life for a chemical stability. So in this case, let's say that you desire that you want to estimate the shelf life at 24 C and a water activity of 0.15 of an aspartame containing food. So what you have to do is collect degradation kinetic data as a function of time. So you track the level of aspartame and how much it's degraded. Do that at 3 temperatures, 30, 37, 45, and 3 water activities, 0.34, 54, and 67. And then once you've got that data collected, use the appropriate kinetic models to calculate your rate constants and hence your half-lives. So from that, from that data you can do a plot and figure out what the rate constant is at any given combination of conditions, and then from that, under those conditions, you can figure out how much time did it take for you to get to where you had experienced 10% loss. So now we have the data set up for being able to do our calculations and figure out what our Q10 value is and what our QA value is. So first of all, if we plot temperature versus the natural log of the half-life, and again the half-life coming from the rate constant that you determined by using the appropriate kinetic models. In this case it was a first order kinetic model. Now if you plot the natural log of the half-life versus temperature, you can get the Q10 value from the slope. So the natural log of the Q10 divided by 10 is equal to minus the slope. So from that you now have your Q10 value that's going to apply to aspartame degradation in this particular material or product. So just a note there, so at shelf life at 0.34 water activity and 30 C is 19 days. The shelf life increases by 4.25 for each 10 degrees C decrease in temperature. Thus the predicted shelf life at 0.34 and 20 degrees C has an increase by a factor of 4.25, so going from 19 days to approximately 80 days. And so you'll notice here that small temperature changes can have big effects on the product shelf life. That was only a 10 degree change, but it has a huge increase in the amount of shelf life by lowering that temperature. Now if you plot from the data that you've collected, you plot the water activity versus the natural log of the half-life, then the slope, you can use the slope of that plot to figure out what the QA value is. And the natural log of the QA over 0.1 is equal to minus slope. Then you solve for the QA value, and now you have both your Q10 and your QA. So this QA value means that at 0.3, if the shelf life at 0.34 and 30C is 19 days, then the shelf life increases by 1.54 according to our QA value we just determined in the previous slide. And so then it will change for every 0.1 decrease in the water activity by 1.45 times. Thus, you predict your shelf life at 0.24 water activity in 30C, so a 0.1 change in water activity is going to be 1.54 more than 19 days, which is approximately 29 days. Now, what do you do when you want to know both the effects of water activity and temperature, or you want to predict what the shelf life is going to be at a different water activity and a different temperature? So if you know that and calculate based on data collection that the time to 10% a 10% decrease in the amount of aspartame, and again you're going to identify what that particular value is for your given situation. What is the condition that causes shelf life to end? But based on those calculations, you can figure out what the shelf life is going to be for that given conditions using the rate constant that you determined using the original data collected. So in this example, at 0.34 and 30 degrees C, you had a shelf life of 19.2 days. In other words, it took 19.2 days for the aspartame concentration to have decreased by 10%. And that's based on a Q10, or it helps us to learn that there's a Q10 of 4.25 and a QA of 1.54. Now if you want to know the shelf life at 24C, but the water activity is the same, then you just simply do the calculation with the Q10 value. You take what the time to the end of shelf life is under the initial conditions or the standard conditions, and then you figure out what the change in temperature is. So from 30 to 24 is a 6 degrees C change. So then you multiply what your original shelf life is by the Q10 factor raised to the power of what the difference is in the temperature divided by 10, and now you get your new shelf life as 45.7 days due to a 6 degrees lowering in temperature. Now what if you want to know the shelf life of a water activity of 0.15? So we're going from water activity of 0.34 to 0.15 with the temperature remaining the same at 30C. So you do essentially the same type of work, except in this case you use a QA value and you raise it to the power of how much the water activity has changed divided by 0.1. And from that you get 43.6 days. So lowering the water activity by 0.19 caused the shelf life to raise to 43 days from 19 days. Well, now what if you want to know what the water activity or what the shelf life is going to be under both a change in water activity as well as a change in temperature? So both of them have changed. So you start out with 0.34 water activity and 30 degrees C. What if you've dropped to 0.15 and 24C? So now you use a technique that combines both the QA and the Q10 factor. So you take the original shelf life, multiply it by the Q10 factor raised to the power of the difference between the temperature, and multiply that again by the QA factor raised to the power of how much the water activity has changed. And by combining those, multiplying, then you can get what the new shelf life is going to be, having changed both the temperature and the water activity. Shelf life is increased to 104 days. So you can see that both the water activity and the temperature do have an effect, and they have a separate effect, and they also have a combined effect. And so if you only account for one of them, like temperature or just water activity, then you're missing part of the story. And this gives then the principles, techniques that you could use to be able to, if you've identified what the QA and Q10 is for your particular product, given a particular degradative reaction that it's susceptible to, once you have those values in place, you can then do a prediction about how long it's going to take until what you've deemed as the end of shelf life due to that reaction, and or any types of conditions that the product may be exposed to. So in conclusion, Water activity can be used to control and model microbial growth, and we've set up the principles for how you do that. The information is there and available for how you would set that up and why water activity does control microbial growth. If you want some more information on setting up that modeling, I would reference you and encourage you to go to the paper that was referenced in the talk by Cindy Stewart. You can also use water activity to predict shelf life based on there being a chemical reaction that causes the end of shelf life. That can be done using a QA, Q10 type of strategy. Great news, we looked at lots of math and lots of calculations, but the good news is that we've already built all of these into an Excel sheet where you can just plug in the values that's specific to your product and the calculations will be done. So in that Excel sheet are templates that can be used to try and set up and do some chemical stability modeling, QA, Q10. So all you have to do is collect the data that's specific for your product at the different temperatures and water activities, and everything's set up for you to determine your rate constants, figure out your half-lives, and then determine your QA, Q10 values, plug in the new conditions that you want to check, and it will tell you what the shelf life will be under those conditions. If you want to find some more information about looking at chemical stability and modeling it with water activity, I'd reference you to Chapter 7 of the Water Activity in Food textbook. If you do work with water activity and want to learn more about it, I would highly recommend that textbook as an excellent resource. And if you are interested in the Excel sheet that does these calculations more in a way that's already been set up, you just simply need to contact me by email and let me know that you're looking for the Excel sheet that was mentioned, and I'll be happy to provide that. We have lots of other things built into that Excel sheet that you can use for doing modeling, for physical stability as well, for packaging, for investigating glass transitions, all within that Excel sheet. And I'd also encourage you to join us for our Water Activity 301 series that talks about water activity and physical stability and the modeling and work that can be done in that area. And so with that, I will thank you for your attention and wish you the best of luck in the work that you do.